Jason's a very valuable person to talk to because he has a deep background in applied mathematics. And that's, of course, one of the strengths of this week is we have people ranging from applied mathematics all the way to physics and everything in between. So he's going to be giving us his perspective on adaptivity and fast algorithms without tensor networks.
Okay, thanks, Miles. So sorry for my title. But when I was invited here, I told the organizers, I haven't really worked much in this topic. I've sort of observed peripherally and participated peripherally. So this is what you get. But I will sort of have QTT in particular in the background in the talk. So we've heard a lot about QTT already, of course, with TCI. This has really come up quickly as a promising tool for representing and doing operations on functions that have interesting, intricate structure. But I would say kind of at least in the corner of the world that I'm coming from, the properties of this tool are not yet fully understood. In the sense of, I'm going to start a timer so I know how much time I have. In the sense of sort of the advantages and disadvantages compared to other state-of-the-art methods, whether there are problems that sort of truly QTT can address that we don't have other methods for, and so on. So I just want to note at the beginning, I think there's a really important distinction kind of in this world of tensor network methods between low-dimensional and high-dimensional problems. In high dimensions, there's less competition. So I'm focusing here on kind of the low-dimensional case. So I probably don't even need these slides because we've already, the authors of all these things are largely in the room, and we've seen these results already in many cases. QTT can represent functions with interesting structures. Here's an example of representing vertex functions where we sort of have, this is a zoom in from left to right. We have these kind of localized features in the middle, these edge-like structures. And QTT does a good job at kind of representing them efficiently. Functions that oscillate extremely quickly and decay. This is like a zoom in of a rapidly oscillating function. Here's a Green's function in momentum space with, again, these kind of localized edge-like features and a function with sort of near singularities. There's been a lot of interesting work with the current rate of one publication per week, it seems, at least in the past couple of weeks, on non-equilibrium Green's function methods, which are functions which sort of have oscillations and decay with some localized features as well. And we just heard this morning about incompressible Navier-Stokes equation and saw these very images. So that's sort of the world of PDEs. So given this growing list of impressive examples, it's valuable, I think, to ask the question sort of how QTT compares to other state-of-the-art algorithms for similar computational tasks. And I should say Michael Lindsay's talk this morning was a great introduction to this, and I think he scooped some ideas in my talk, but I'm going to go into a little bit more detail about sort of certain aspects. In particular, what are some of the other algorithms out there? I think there is significant overlap, which doesn't mean necessarily total overlap, but significant overlap between some of the target tasks of QTT and problems in applied math that people have been thinking about for a long time. And I just want to focus on sort of like one or two of these ideas, which is not everything QTT can maybe do, but some of it, which is efficient representation of localized functions, for which traditionally adaptive data structures have been used, and how to do fast operations on these functions, like solving differential equations or applying non-local integral operators, on top of these adaptive structures, which is a challenging problem. So the question is sort of, what are the state-of-the-art methods to compare against that go beyond, uniform grid methods and things like this, to understand what can QTT do that other methods can't. What are the methods that should be benchmarked against? So, I intended this as a sort of pedagogical talk, mostly, to just, to tell people about what some of the other ideas floating around out there are, like the flavor of those ideas, some things to start thinking about in terms of benchmarking. And I will, since I will sprinkle in example kind of applications of these ideas for my own research. So let's start with adaptive function representation. So people want to do things like solving PDEs on sort of intricate geometries with large features, and you can't even see, like very localized features as well, multi-scale problems. So I have a sequence of pictures which were provided to me by Manas Roch, who used to be with me at Flatiron, using this software called FMM 3D BIE, which implements the fast multipole method using boundary integral equation reformulations of PDEs. And we'll see what FMM is, at least. So we want sort of PDE solutions with multi-scale features and complicated geometries with automatic grid refinement and controllable high-order accuracy. These are things that people have wanted for a long time. So here we see this plane, some simulation of sort of wave scattering. Here's some kind of capacitor with these intricate interlocking features, and an electrostatic simulation requiring a lot of grid adaptivity to deal with sort of near singularities. Another interesting geometry with wave scattering. This is fluid dynamics. This is sort of Stokes flow. These very thin rings sedimenting in a Stokes fluid. Some kind of simulation of a superconductor showing off. I think they're trying to show off that they can deal with genus larger than one systems, and another kind of intricate multi-scale geometry. So all of these simulations are sort of done with high order accuracy, controllable accuracy. That's what people want to do. So that's why one of the reasons people think about automatic adaptivity. And I want to just tell you kind of what the basic algorithm that I have in my mind of automatic adaptivity is. If you call MATLAB or SciPy's integrate, this is basically what it's doing. Yeah. Sure.
So when you say high order accuracy, are you mostly thinking about time, or is it applied to space, or both?
Well, here, these are all basically, well, they're not all static situations, but let's say time and space. But let's say space. Let's think about space in this talk. But yeah, that just means that I can get more digits. I can get an extra digit for a small amount of additional effort. So things like Gauss quadrature and Chebyshev methods allow you to do this. So let's think about automatic adaptivity. Let's think about interpolation or integration, at user-prescribed accuracy epsilon. I'll just take integration for concreteness, but you can do very similar things for interpolation. And this algorithm sort of has two main ingredients. In the case of integration, it's a high-order quadrature rule, like Gaussian quadrature, and then you need a local error estimator. So let me explain what I mean. So I have a function. It's funny, I almost drew exactly the same function as Michael earlier. But you have a function, and it has some localized feature. We want to integrate this. What do? We put down a 4-point Gauss quadrature, okay, on a single big panel, and we approximate the integral using this thing, and then we do the same thing with two kind of child panels, each having 4 Gauss quadrature nodes, and we add the two results here and compare them to the results here, and, well, they don't agree. 4 nodes isn't enough. So we split again, okay, and we repeat this procedure with these. So compare this plus this to this. And maybe we find that, okay, these agree now, because it's pretty smooth there, but on the right side we don't agree, so we split the right side, we keep going until we're done. Okay, so this automatically sort of found the localized features of our function. It's completely automatic. We can get machine precision if we want. You can code this up in less than 50 lines of code. Very simple algorithm that automatically sort of finds localized features of your function. So an important thing to note about this algorithm is if we have some feature of width eta with a uniform grid, we would, of course, need 1 over eta points to resolve it. The adaptive grid does it in log 1 over eta points because we have these kind of dyadic refinements towards this feature. So that's an exponential speed up as well. Good. Okay, and if you want to do sort of function approximation, you can replace the Gauss quadrature with Chebyshev interpolation, and you can estimate the error by sort of sampling points off grid, and it's basically the same thing. Okay, so let me tell you about an application from physics, which is Brillouin zone integration. So we know from block theory that if we want to solve the Schrodinger equation in a periodic potential, we can write down a momentum-dependent Hamiltonian h of k, and we get the eigenvalues as a function of k form these periodic bands. Okay, so here I've shown the bands for a 3x3 Hamiltonian. This is how you get band structures in physics. And as many of you know much better than me, many quantities and calculations that you want to do involve integrations over this momentum space, which is called the Brillouin zone. For example, computing the Green's function, from which you can get the density of states, is given this way. So here I've just written this in terms of its eigenvalues. And let's just stare at this for a minute. So what happens? We fix some omega. And when omega sort of hits an eigenvalue of h of k, we get a near singularity, which is smeared out by I eta. And in many sort of real simulations, for example, the DMFT simulations that we like to do at Flatiron, the role of this I eta is replaced by a self-energy, which is a physical thing that actually sort of physically smears out the integrand. So here, so this is the integrand for this system. And you can see that like these omega slices each correspond to kind of one of these manifolds here. So you get these sort of three components that give you this integrand. And so you get these sort of nearly singular surfaces in 3D of width eta. And we want to go to very small eta. Our self-energies could have eta down to like 10 to the minus 4, let's say. So this is a challenging problem for integration. There are more complicated Brillouin zone integrals, like we've done some work on using similar ideas to compute the optical conductivity. The integrands get worse, but this basic structure pretty much survives. So let me tell you about 3 integration methods. Here's a simpler example, but same idea. So what would happen if we integrated with a uniform grid? Well, we need sort of O of 1 over eta points per dimension to capture eta scale features on a unit scale domain. In 3D, we get 1 over eta cubed complexity. Not complicated, but bad, right? If eta is 10 to the minus 4. So what about another scheme? So if you sort of take the algorithm in 1D that I told you about and try to generalize it to 2D or 3D, what you might do is something like this. So, okay, this red circle is supposed to be that red circle. And you might sort of start chopping in 2D boxes into 4 smaller boxes, okay? And run basically the same algorithm. So that would give you a grid that looks like this. And then you could use a product Gauss quadrature rule on each box. And we call that tree-based adaptive integration. And let's try to understand the computational complexity. Well, how big are our boxes? Eta, diameter eta. And how many of them are there? O of 1, because we have to cover sort of a circle, an ellipse here of arc length 1, okay? So in 2D, we would get O of, okay, this is the actual grid you would get if you run this. So in 2D, we get basically O of 1 over eta little boxes. And in 3D, you have to cover a surface. You would get O of 1 over eta squared. And then there's also a logarithmic factor that comes from refining in this direction. Okay, so you do a little better, but it's still not great. And it looks morally incorrect, okay? We should get some logarithmic scaling because, if you were in the coordinates of this surface, you would just sort of like put a uniform grid this way and an adaptive grid this way. Okay, anyway. So it turns out it was kind of surprising to us, but there's something much better. And it's just as simple, but a completely different scheme. You just call 1D integration in a nested manner. So you sort of pull in the ky integral, and you write your integral as an integral of kx, and each integral of kx is an integral of ky. And then you call 1D adaptive integration on each of those integrals. The points that it gives you look very different from this. So let's understand the complexity again. So let's look at this function I2 of kx, which is sort of the outer integrand. You get this by just integrating these slices in ky for each fixed kx. So what are the points where this as a function has localized features? Well, it's only at these kind of tangents to the curve. Whoops, sorry. It's only at these tangents to the curve. Nothing interesting is happening here. So you get these localized features of width eta here. And so, okay, you can use adaptive integration, and it will resolve this function with log 1 over eta points. Okay, so then what's the cost of doing the doing the ky integral for each fixed kx point? Well, you're just doing these integrals. Okay, there are two localized features of width eta, log 1 over eta again. So the complexity is log 1 over eta times log 1 over eta. In 3D, it's cubed, and this is much better than this. Okay, so it turns out that the iterated adaptive integration is much better than the tree-based adaptive integration, which I don't know, when we realized that as applied mathematicians, we were a little bit confused about why we didn't know that already. But these functions have a very particular structure. But that works, so we like computational complexity and timings. Let's see some. So for this simple example, this is just the tree-based method versus the iterated method. And you see that we sort of always win. We get our nice logarithmic complexity. I didn't even put the uniform grid method on here. It would be worse. Now we go and compute a density of states of some material. Here we actually use adaptive frequency interpolation, okay, in the frequency variable. Each frequency point calls 3D iterated adaptive integration. This is the frequency grid you get. So it's adaptivity all the way down. So we can resolve these sort of localized features in frequency. Timings at a single frequency point. Now I'm comparing the periodic trapezoidal rule, which is our name for uniform integration, with IAI. And we see the cubic scaling versus our logarithmic scaling. This is sort of where uniform grids ran out of memory. And we can go down to sort of eta less than 10 to the minus 4 in like 10 seconds for a 3D problem. And here's the timings for the full density of states at eta 10 to the minus 3. Computing this whole thing took like 20, 30 minutes on a single core. Okay. So now let's, I think I can slow down a lot. So now let's make things a step more complicated. That's pretty simple, where we just want to integrate a function. What do people do when you actually want to solve differential equations or integral equations on top of these adaptive data structures? And I just kind of want to give you just a flavor of this. So in applied math, we always sort of go back to our prototypical PDE, the Poisson equation. So that's what I'll do. Let's consider the Poisson equation with a density rho, which is compactly supported in R3. Okay. And what's the simple, naive way of solving this? Well, you Fourier transform both sides. You get this xi squared symbol of the Fourier transform coming out. Xi is the Fourier transform variable. And then you divide by xi squared, and you take an inverse Fourier transform, and that gives you sort of a Fourier transform expression for the solution, which suggests an algorithm. I'll take a fast Fourier transform, an FFT, multiply by the symbol, and take an inverse FFT. There's a bit of a lie here, which is that if you just go and do this, the FFT sort of implies periodic boundary conditions. So you'll get all of these periodic images. And even if you zero pad a lot, the images decay very slowly because it's a Coulomb interaction, and don't do this. There are professional, very effective ways of correcting for this, which is basically to figure out what's the correct symbol of the Fourier transform to use in the free space case, and you'll crush that problem. But that's just a side note. So there's some modification of this that will work. And of course, the FFT is sort of running on top of a uniform grid. So this is an inherently uniform grid type of method. So what happens if rho is highly localized? So the problem you get is really just a matter of Fourier analysis. It doesn't have anything to do with numerical analysis. Rho is highly localized. That means you have very slow decay in the Fourier transform domain. You would need a very fine grid in space and sort of a gigantic box in the Fourier domain. Okay, and there's something called the non-uniform FFT. So you might think that fixes this problem. It doesn't. This is a problem of Fourier analysis. The non-uniform FFT is a wonderful algorithm. It's not for this. You need adaptive methods. So of course, there are finite difference and finite element methods, which is what kind of most of the world, vast majority of the world uses. Those methods have their set of problems and challenges. I'm going to talk about kind of the integral equation philosophy, the integral equation approach to this, which has its own challenges, but that's what I'm going to talk about. The integral equation approach is write down the solution. Okay, we know the fundamental solution of the Poisson of this equation. It's sort of 1 over r, 1 over distance. So you can write down in space an integral formula for this solution. Good. So this looks kind of bad because, well, we have a singular kernel. Rho is extremely localized, I told you. So let's talk about the singular kernel. Well, people in applied math have done a lot of work to deal with the question of singular quadratures. How can I integrate singular functions accurately? So we're going to sort of treat that as a solved problem. Okay, you can come up with some quadrature weights that will handle this singularity. So then what I have to do is sort of put down a grid, perhaps in the manner that I explained at the beginning of the talk, in this sort of automatic way, which resolves rho. All right, and then I apply my singular quadratures, and I get a discrete math problem of this type. So xk are going to be some grid points which have adaptively resolved rho. Wk are some quadrature weights which sort of handle the singular kernel. And let's say, to keep things simple, that I also want to evaluate the solution at the same grid points as I've represented the data on. And for the Poisson equation, that's probably a good idea, okay? Because the solution will sort of be smoother than the data. Good, so we end up with this discrete problem. And this is really now just the problem of calculating the potential of a collection of point charges on all of the other point charges, right? So I'm just writing this Wk rho k as oh, this should be Qk, sorry. Qk, okay? So it's this nice sort of classical electrostatics problem. But of course, the scaling of doing this calculation is O of n squared, where n is the number of points because, well, it's a matrix vector multiplication, right, at the end of the day. So can this cost be reduced? So people have had many ideas about this. One of the early ideas, which I'm going to very briefly tell you about, is the fast multipole method, which was sort of exactly, again, that's Qk, which was exactly thought up to solve this problem. How do we do this sum to epsilon accuracy? This is an algorithm from Greengard and Rocklin in 1987. So yeah, in an earlier version of this talk, I actually had more slides explaining the fast multipole method, and then I cut it down. So oh well. But let me just sort of give you the basic ingredients that go into how you do this. Some facts. if I have a cluster of point charges, the potential induced via this sort of point Coulomb kernel, the potential induced by those point charges far away is well represented by a multipole expansion. Okay, we know that. So there's a multipole expansion that's sort of valid in a sphere outside the cluster of particles. If I'm again a cluster of particles and there's some far field potential that's coming in, I can represent that locally by a local expansion, a Taylor expansion. Okay, so this sort of far field expansion can be represented inside this sphere by a Taylor expansion. Okay, and so what the fast multipole method does is kind of organize these translations of multipole coefficients to local coefficients using an adaptive tree in a hierarchical manner, such that big clusters of particles that are sort of very far away from each other get handled, this information gets shipped at a coarse level of the tree, and clusters of particles that are closer together, the information gets shipped at a finer level of the tree. That's the basic idea. And another basic idea is that you can basically build a multipole expansion at a fine level of the tree, and then you have a few multipole expansions, and you can merge them to get a multipole expansion of a bigger cluster at a coarser level of the tree, and you can do the same thing with the local expansions in the other direction. Okay, so it's a cool algorithm. It's pretty complicated, but you can learn about it and understand it. In the end, sort of surprisingly, you get O of n complexity. Okay, you do all the counting, you get O of n computational complexity at fixed epsilon. Okay, it's not exact, like the FFT is an exact fast algorithm. Fast multipole method has an epsilon, but it will guarantee epsilon accuracy, and it will do so efficiently in epsilon. So with these discretization ideas plus these fast algorithm ideas, we get an optimal complexity fully adaptive Poisson solver. And this idea has had many, many descendants, including for other PDEs, including sort of wave-like problems, time-dependent problems, but that's sort of, a fundamental idea. Yes, I think that's all I want to say about that. So, good. Sure. Yes. Well, so yes. So the original classical fast multipole method is for that kernel. People have, of course, designed other methods, similar methods for other kernels. Typically, you are sort of strongly using information about the kernel. There are more modern variants that, for example, the kernel independent FMM, which only requires that your kernel is the fundamental solution of some PDE, but it doesn't care what the kernel is. And then there's another style which gets into things like hierarchical matrices, which are sort of, let's say, purely linear algebraic versions of this kind of idea, where you actually figure out if I look at the 1 over, if I look at this kernel as a matrix, how can I sort of block up the matrix and represent subblocks with a low rank format to sort of reproduce essentially in linear algebraic language what this algorithm is doing. Okay, that's a long-winded answer to the question. But yeah, you need some structure of the kernel, basically. Okay, so here's another application from my research, which many of you probably know about, which is computing this electron repulsion integral, or ERI, 4-index tensor, VIJKL. So this is the definition. Here, these phis are orbitals, single particle orbital basis functions. And you can, so yeah, I mean, basically this comes up as an ingredient in electronic structure calculations involving some many-body interactions, for example, the GW method. This is sort of an input ingredient. So if we take this, here I've just rewritten this by defining rho ij as phi I times phi j. These are so-called pair densities. And you see that computing this amounts to sort of solving the Poisson equation for each KL and then taking an inner product. So we're sort of back to the problem that we saw before. Of course, the issue is, this is a big object. Storing this is hard. Solving all of those Poisson equations is expensive. People don't want to sort of deal with this directly. So an algorithm that some of my colleagues have developed and used, well, they didn't develop it originally, but have been working on it and using it to handle this situation is interpolative separable density fitting, or ISDF, which starts by essentially making a low rank approximation of these pair densities. Okay, so for the people who know what I'm saying, this is an interpolative decomposition. It's a row interpolative decomposition. But basically what you're doing is there's a purely linear algebraic way of representing rho ij in terms of an auxiliary basis, zeta, which can be determined. And it turns out that the number of basis functions, for reasons that I think you can essentially prove, is O of m, O of the number of orbitals, rather than m squared, which is the number of rows. Okay? So you can come up with an auxiliary basis for these rows.
Zeta, what are they?
These zetas are the auxiliary basis functions, and they can be determined by basically doing an interpolative decomposition of this, thought of as a matrix with columns ij and rows x.
So you construct them.
Yes, using linear algebra. Okay, so so that's that. Why do you want to do that? Because when you take this and you plug it back in here, and you turn, one or two lines and rewrite the rows as phis, you get this expression. I guess this should be approximately equal to, but in a controlled way, where you have this v mu nu in the middle. And v mu nu looks like our ERI tensor, but with the rows replaced by zetas, and there's a smaller number of zetas. There's O of m instead of m squared zetas. So that's a good thing. That's a good thing for computing this. This is also a good thing for downstream calculations because you've completely separated the I, J, K, and L indices. And you can imagine that when you want to go contract V with something else, that's a good thing. And it gives you things like cubic scaling GW methods. Okay, so I guess I am talking about tensors a little. That's my little tensor part.
It's R cubed.
What's R cubed?
The storage for VIJK, it's n cubed, or it should be n cubed.
Well, it's R squared, right? The storage, because you just have to store V mu nu. Right?
I think the chemist would agree. Like, did you try that on real?
Yeah. Is that wrong? Yeah, no. I mean, it's just that the number of mu's is certainly O of m. Oh yeah, this is better than classical density fitting. This is a sort of newer algorithm. Yeah, relatively recent, I guess. Who wrote this down? Was this Leshing? I don't know. I should ask you. It's older. Okay. Yeah, but yeah, you would get m squared storage, and then things like computing the GW self energy are O of m cubed. Yeah. Yeah. So okay, that's good. And then you can guess the rest of the story. Okay, this is called this tensor decomposition format is called tensor hypercontraction. Okay, cool name. And it's useful for downstream operations. So you have to perform now O of m Poisson solves, which is still a good amount of work. And of course, previously, this was done with uniform grids in the FFT, like I told you about at the beginning. And so this is a significant limitation when phi is localized. for example, if you want to do all electron calculations, involving core orbitals without pseudopotentials, okay, which people would like to do. So, okay, it's obvious what we did. This was sort of low-hanging fruit of just clicking pieces together. Usually it's not that easy, but this time it was. We build a machinery to approximate all the phi's on sort of an adaptive piecewise Chebyshev grid using the interpolation version of exactly the algorithm that I showed you at the beginning. And then we use sort of a very recent modern descendant of the fast multipole method called DMK, which is very fast, sort of achieves very high throughput in terms of points per second. That's how they measure things because they're linear scaling algorithms. 2 million points per second, roughly. And that's what we did. So let me show some pictures. This is sort of the adaptive grid that you use to resolve this dimer. You can see a slice through the grid where you kind of see both molecules and then the structure of the orbitals within the molecules, okay? We're using, in all of these, we're using sort of all electron bases. This plot shows you that, so these are sort of curves of error versus essentially the compression factor in the ISDF of molecules with sort of more and more localized core orbitals going down the periodic table. And this shows you that the compressibility is basically just as good, even as you have more and more localized functions. This is sort of system dependent. Sometimes it can grow very, very weakly. Here are timings. Let's say for 3 digits for an all electron basis, where the largest Gaussian decay coefficient is 1 million. We need less than 1 million adaptive grid points for a problem that if you used a uniform grid, you would need between 16,000 and 32,000 cubed grid points, okay? So, less than 1 million grid points is the amount of grid points in a less than 100 by 100 by 100 uniform grid, okay? Which you couldn't do much with. So this is for some very simple case. And then here are some timings, which basically show that for this very simple molecule, the timing of the ISDF step and the Poisson solves is comparable. And it turns out that basically, as you scale the system size, the cost of the Poisson solves actually scales slower than the cost of the other step, the decomposition of the row. So this essentially means that for large systems, we will get full adaptivity at essentially no cost, okay? Measured in terms of number of points, okay? So you get 1 million points, you can put them in a uniform grid, or you can put them in a fully adaptive grid. The cost is going to be quite similar, okay? Good. So just to wrap up, I think, I'm just trying to tell you about some of the other kind of state-of-the-art ideas out there, which I think it would be useful to sort of start to compare QTT against on kind of specific, well-defined computational task. QTT, I think, perhaps does lots of things, not just the tasks, the type of tasks that I showed you, but maybe starting with kind of adaptive rather than uniform grid methods is a good starting point. I think there are many possible advantages of QTT. Perhaps computational complexity improvements for certain classes of functions are the same complexity with better prefactors. I think, people mention a lot, and I think it's true, flexibility, convenience, composability, without paying a large price and cost. Perhaps new domains of applicability, discrete problems, maybe sort of not super high, but medium dimensional problems. It would be interesting and useful, I think, to kind of clarify what the place of QTT is with respect to these kind of metrics. So the last thing I want to say is it's always tough to compare algorithms, and I've written lots of reasons why, but it's easy to do half of the comparison, okay? You can try to write down the computational complexity of your algorithm, and you can time your algorithm, right? And then the next person who's coming along and sort of comparing their algorithm to your algorithm has a lot of information. Of course, wall clock timings, we know computational complexity is very useful, and to sort of an applied math brain, knowing the computational complexity already tells you a lot about what's actually happening, okay? Wall clock timings are imperfect, they're implementation dependent, they're computer dependent, they require you to make sort of a good faith attempt at coming up with a reasonable optimized implementation. But if, for the same task, my algorithm took 10,000 seconds and yours took 10 seconds, there's information content in that statement that's useful. So yeah, let me just acknowledge collaborators. These are the characters who worked with me on the Brillouin zone integration project I mentioned. Many people at Flatiron. Lorenzo is a PhD student at MIT. And then these are the people who worked with me on the adaptive ISDF project. And this was sort of a nice collaboration between half mathematicians and half physicists. So, okay, thank you.
Let's thank Jason. Great, okay, questions? I see.
Thanks for the talks. I'm acting like a historian in this. I remember we had a project with Denis Zorin from NYU, and yeah. So first of all, everyone working with these multiple codes, and not everyone, many people working with multiple codes actually quit doing science after that because it's really difficult to write and it's very difficult to.
That's for sure. But someone else has done it for you. So
yeah, but that was actually one of the NYU codes, and our guy, he was taking it and then said, no, and I rewrite it from scratch. But anyway, and he had a PhD student, Corona was his last name, and he did some work on QTT solvers for integral equations and complex geometries. I think that was, they had some comparison with, that was another fast multiple code, but that's close to KFMM or something. So maybe that's also a reasonable reference.
Yeah, I've been meaning to look more closely at that paper.
Yeah. But it's literally, they took some of the summations, did it in the QTT by clustering, because the main problem, if you apply it to uneven distribution of particles, is that you have to introduce somehow this multi-index numbering of the particles, and you can do it, for example, just by sort of splitting into two. Left part gets 0, right part gets 1, and so on. That would be like a binary number, and then use QTT on top of that. But I can show you the reference. Yeah, I think this guy also left to some industry afterwards, but still it was a good paper, I think. Okay.
Yep. Cool.
Okay, another question, like young people have questions.
To come back to the end, like we also have been looking at this Coulomb integrals. And so the basis set that you showed and that almost everybody is using in chemistry are this Gaussian basis set.
Yeah.
Which people use because in this case, actually, you can calculate everything analytically.
Right.
But so did you close the loop entirely? Like, so did you look at the other integrals that you need to get, like the phi, Laplacian phi, and all these things? So because
is the question, can we use other basis functions?
No, I guess you can.
We can. We were just lazy.
Okay.
But yeah, the method is totally agnostic to the basis. It doesn't care.
Yeah. Now the question is how far did you? So because there is so there will be a talk by Nicolas Joly tomorrow, and she will show that there is a huge accuracy problem in chemistry due to the fact that this basis set sucks essentially.
Right.
And they do because people have been stuck with Gaussians forever.
Right. So yeah, that was part of our motivation.
Okay, but so did you go all the way to chemistry, or you just did this on the? You need more integrals to have the full problem. Like you need the for instance integral over just in 3D of phi I Laplacian phi j.
I see what you're saying.
And all these things.
Yeah, no, we just did this one, but I would think this one is the hardest. I mean, that everything else is local. Like if you have a differential operator, it's a local operator. This is the non-local one.
No, I just wanted to see.
Yeah, no, this is all we did, and I think sort of for, I mean, we were working with Miguel Morales and Xian Anye, who are doing, GW. They're building a big GW code, so that they're sort of the customers there. And
but the fact that it's M2 is actually big news because they are all stuck with M3 code.
Yeah, right. That's why they're building a big new GW code, because they're implementing the cubic scaling
But
version.
even for the Gaussian orbital people, they would love to do that.
Right. Yes,
And
we
the code
agree.
is very GPU accelerated as well, so it's pretty awesome.
Right. It's a good code.
Cool. So we have time for one more question, I would say. So who in the back has a good question to ask? Maybe I just can pick someone. Okay. I mean, actually, I had one too, but okay, last chance before I ask mine. All right. I mean, I had a question that may sound a little odd, but I think it makes sense, which is that you can kind of smell like linear algebra in many parts. Like you mentioned, the FMM can be, I guess, turned into hierarchical matrix, maybe with some losses in places, but I think it's sort of like scaling wise, maybe. And then this one has an interpolative separation. So I mean, interpolative factorization in it. So my question is something like, could these be fit into a more general language as each other and viewed? So like, you know, your title says without tensor networks, but if you view tensor networks as just fancy linear algebra stuff, could there be some kind of way to like say, these are all special cases of more general linear algebra that automatically would give you these, and then maybe even more algorithms could be fit into this framework?
Yeah, I mean, that's possible. I'm not sure. I think like what the cutting edge of the research in FMM-like things, integral equation-like things, is, okay, we all have linear scaling. Now, what can we do to absolutely squeeze down the prefactors as much as possible?
Yeah.
And you know, how much do I do with pure linear algebra? How much do I do with analysis? So people are thinking a lot about those things. That doesn't mean there isn't some completely different idea that's faster.
This one seems like a completely different idea that's more at the linear algebra level, if I understood correctly, right?
Well, so here we're sort of using an FMM-like Poisson solver as a step in this, right? And then there's another step in this, which is this decomposition,
Or like that step,
right?
Yeah.
And that, you know, that's not me. I haven't thought about that. So, but yeah, I mean, there may be kind of a broader framework that like fits things like QTT and hierarchical matrices into a similar framework. There are probably people here who have thought much more about that than me.
If that sounds like something that you would view as like a good direction, or is it maybe a little too naive?
I have no idea.
Great.
Yeah.
Okay, well, online question too. Great.
Okay.
Sure thing. Okay. So one question was, at the beginning, you talked about using an adaptive grid when the function is unknown. In that case, is adaptive Chebyshev preferred for non-periodic functions?
Well, I mean, yeah, adaptive Chebyshev is my method of choice if the function is not periodic. So I don't know preferred compared to what, but I prefer it to almost everything.
Half of the question was, if the function is known, is there a standard approach to adapt the grid based on gradient and curvature information?
I would say in a situation where the function is known and you sort of know what the adaptive grid should be, like you have a singularity and you know you should refine into it, you can be even more efficient by just using that grid and the rest is the same. But take a look at this timing. Octree construction. This is the adaptive grid generation. 2.5 seconds. Oh, and I should have said we did like 1,500 Poisson solves. It was like 1 Poisson solve per second is the speed. So the tree generation is very efficient, typically.
Great.
As long as your functions are not too expensive to evaluate. Okay.
Okay, thanks for the question online, and let's thank Jason again.
Thanks.